for the IV curve, we have V, this is 0, so this is membrane voltage. I'm gonna put mem here. And we have this y-axis, which is current. So the positive is going outward, and then negative is coming into the, it's like inward to the cell. And our usual, like the resting membrane potential will be somewhere like here at like negative 80-ish. So when if you were to draw like a regular, like a line through it, so let's just do it through like here. Okay, I don't have two hands, so it's gonna be crappy, but whatever. So this is just like a regular line, and the slope of this line, which is V, so as we all know, it's like rise over run, so it's like I over V, and we all know V is equal to IR. So if we do the magic, it would be 1 over R is equal to I over V. So it's conductance. And since it's 1 over resistance, so it is conductance. So the slope is conductance. Okay, that makes sense. It's pretty easy. So this line is showing that it has a constant slope, but in reality, when we have, for example, so that is the case when the ion concentration of inside and outside cell is like constant, or I mean like same. Out, actually this is supposed to be in, out. But in the case where it isn't, so where is it? So for a K plus channel, so potassium channel, it has a hour rectification, something that kind of goes like that. It's K plus, and we all know that potassium is higher on the inside. So there will be potassium when the C out over C in is inside is high, so it should be smaller than 0, right? Smaller than 0, okay. And the opposite would be have the inward rectification, which goes like that. And that is representing sodium ion channels IV curve. And C out over C in will be bigger than 0, and bigger than 1, because outside concentration is higher. And let me intuitively explain why that is the case instead of just putting it in the math term. If you think about this curve, the action potential curve, it looks something like that. And so like if it fires and then it goes down and hyperpolarized, and there's a refractory period, and then it goes back to come to its like normal resting membrane voltage. And this increase in membrane voltage is mainly driven by the sodium, and then this coming back down is driven by potassium, and that's probably common knowledge. But if you relate this movement to here, or this phenomena over here, it makes sense because, so let's go back to the potassium. So what is happening here is that when the membrane voltage, the voltage, so membrane voltage is like negative. Actually, let's start with this one because the sodium start first. So when the sodium ion is a negative, it goes up really quickly, which means the conductance is the permeability of the ion is really high, right? Because it's like moving quickly. So when the voltage is negative, so on this left side, the slope or the conductance is really high. And then as it goes up and becomes the positive voltage, positive membrane voltage, we see that the slope is kind of decreasing, right? So it was almost vertical, so it was really high, and it goes like slows down. So that explains the the inward rectification of the sodium ion channel. So it's the exact opposite. So we see that potassium comes down when the voltage is like, let's just say this is like 0, and then from here is like positive. So when the membrane voltage is high, the potassium ions is like acting in, and then it just hyperpolarizes the membrane voltage, right? So at this stage where the membrane voltage is positive, this potassium ion has to have a higher permeability or conductance. So we see that at membrane voltage is like high or positive, we see there's a relatively, I'm exaggerating, but we have really high slope, almost like vertical, and then it shoots back down as almost become flat when it's coming back down to like negative voltage. And yeah. So that explains the outward rectification of the potassium ion channel. So that is kind of like the intuitive reasoning behind why it happens, not the mathematical one.